Okay, great. So yes, I'm Harry Coules, talking to you from sunny Bristol, and I'm going to be talking about this proposed EMAP instrument. So this is a high flux, medium resolution neutron diffractometer that's designed for, well, engineering studies. And I'm going to use engineering as a shorthand here for sort of applied mechanics, structural materials, device level characterization. Stuff that isn't sort of chemistry, functional materials, that kind of thing, big things, effectively. I'm a sort of long-term ENGIN-X user, so thank you to Tung, Saurabh, and Joe for, I've been privileged to use that beamline for the last 10 years or so. Okay, I'm going to talk about the capabilities and sort of strategic needs, also the concept of this beamline, and share some performance characteristics. But this EMAP name, I just want to explain first. So you can see it's styled here, epsilon map. Epsilon is the symbol that we use in applied mechanics to represent strain. So this name means a strain mapping diffractometer. So we've heard a lot about the applied materials science research that goes on at ISIS. Apart from things like functional materials, there's a lot of, well, again, using the shorthand of engineering to mean everything else, a lot of other research that goes on as well. Some of the most important applications are in novel structural materials and in manufacturing processes. So if you want to understand novel alloys, you need neutron diffraction quite often. Similarly, if you want to understand, for example, the stresses in a new additive manufacturing process or in a forming or forging process, you need to use neutron diffraction to do that. What we call through-life engineering as well, so things like fracture mechanisms, failure mechanisms, fatigue, and materials degradation at high temperature. You can look at all of those things using diffraction. And on the subject of diffraction, because all of the materials that we tend to use in mechanical engineering and aerospace, things like that, we're talking alloys, composites, ceramics as well. These are things with quite high elastic moduli. So that means that you need a high resolution diffractometer in order to resolve stress in them within the elastic regime. Also things like device level inoperando studies. So if you're in, well, we've talked about batteries and fuel cells already today, but if you're interested in characterizing them at device level filtration as well, granular media, you might be interested in energy resolved imaging in order to do that. SANS as well for material studies can be quite useful. So what are the strategic needs? Well, again, this has been covered by some of the previous presenters, but from an engineering perspective, there are quite a few things in, for example, offshore wind, new and advanced nuclear that are foci for the government. Just recently the government put out a 10-point plan for green industrial revolution, and that sort of feeds into BEIS's strategic priorities. It feeds into UKRI's strategic priorities, and quite explicitly there's some of these energy goals that will be defining the necessary foci for research over the next 10 to 20 years or so, many of which will rely at least partly on neutron science. So for example, if you want to understand how materials behave at high temperatures over long time scales in a generation 4 nuclear reactor, you might need to use diffraction to do that. Or likewise, if you want to know how the welding process that you're using to attach this wind turbine to its monopile, how that is going to fare over 20-25 years of exposure into dynamic load, wave loading in the North Sea. Again, diffraction can help you with that. And yeah, in things like zero emission vehicles, device characterization, inoperando studies on batteries and fuel cells, etc., is really important. So that's the context. ISIS's existing capability includes ENGIN-X for diffraction, IMAT, just commissioned in 2017 for imaging. So if you wanted to do some energy resolved imaging, then you can take your component or device or plant in some case, or cultural heritage item over to IMAT and do it there. Of course, there are lots of other beamlines used for engineering type studies, chip IR for irradiation, for example. But the important thing to recognize is that there's very high demand for both of these. There are other instruments in the engineering kind of optimized instruments in the world. For example, ENGIN-X's design is similar to that of Vulcan at SNS and Takumi at J-Park, which are also very strongly oversubscribed. And we're really interested in looking at an instrument that bridges the gap between these two capabilities, high resolution diffraction optimized and imaging optimized. But at the same time, there are other beamlines which are either being proposed or being commissioned worldwide, which focus kind of in the middle here, but more towards structural material science. So BEER at ESS, for instance, is focused on kind of engineering material science studies. BL08A at CSNS will be as well. And the concept of EMAP is to have a diffractometer which bridges this gap, but also focuses on component scale stress mapping, capability for in situ manufacturing studies, big stuff basically, rather than looking at structural materials themselves, although we'll have capability for that as well. So here's an overview of the design. In concept, it's similar to ENGIN-X. We have, so here's the beam guide here, sample in the middle, and we have these two detector banks at 90 degrees. The idea behind EMAP is to really go for much greater flux than is available on ENGIN-X. This will come at a slight cost in terms of diffraction resolution, but it's also an instrument that's being designed to be very flexible. So it will have a high flux mode and a high resolution mode, allowing you to basically choose between, if you want to map stresses in a component around, say, a weld, the residual stresses that are left by that in great detail quickly, then you can build up a map of that quickly. Or if you need to do in some kind of in situ manufacturing study, looking at, say, how an additive manufacturing process is affecting the stress buildup and phase transformations in a material, you can do that quickly well using the high flux. Okay. So yeah, this is just the same kind of thing, really. We've got just a comparison of EMAP, and you can see that its design is very much influenced by ENGIN-X, which is, has been operating quite successfully. The issue with ENGIN-X, though, is it's much more optimized towards high diffraction resolution, and yeah, that does come at the cost of flux. So the limitations of ENGIN-X are firstly oversubscription, but most importantly, that it doesn't have the required flux to do a lot of things that we would like to do. So here's the situation of EMAP. The idea is to put it next to IMAP on target station 2. It's got this 64-meter long beam guide away from the moderator. So and it has this. It will have choppers similar to ENGIN-X. In terms of performance characteristics, this is the flux as a function of wavelength. So ENGIN-X, you can see here, has a much lower flux. By the way, these two lines are the two different modes that EMAP is being designed for. So this orange one is the high flux mode. This red one here is the what's called medium resolution mode. So it's the higher resolution mode. And if you see here in terms of flux gain over ENGIN-X, we've got a very significant flux gain over the whole wavelength range. For most engineering studies, we tend to be interested in the wavelength range kind of 1 to 3.5 angstrom. So we're getting a flux gain of, well, even in the sort of high resolution mode, kind of between 4 and 10 times across that wavelength range, and much more if you're using the high flux mode. So yeah, of course, this comes at a cost in terms of diffraction resolution. So here are some simulated peak profiles. All of these from neutron transport simulations, of course. So this is the Syria 220 peak for ENGIN-X, and then simulated for EMAP, showing the intensity gain. If we normalize it to the intensity available on ENGIN-X, you can more clearly see the peak profile. So we've got a broader peak profile for EMAP, but in this higher resolution mode, the rising edge is not too bad. It's actually quite similar to ENGIN-X's one. And this peak broadening is obviously significant, but its significance differs depending on what kind of materials you're looking at. And in engineering, we tend to be, if you're interested in structural materials, usually these are single, maybe dual phase materials, relatively simple structures. So if we take a typical engineering material, this is BCC iron, then you can see that this peak, these wider peaks are not causing peak overlap in this case, and they wouldn't for most engineering materials, which is quite nice. We sometimes do want to cope with multi-phase materials as well, but say many phase materials or materials with very complex structures are rare. In terms of the despacing resolution, again, this just illustrates the reduction in despacing resolution compared to ENGIN-X. But the point here is that that's a trade-off that after having run ENGIN-X for a number of years, it seems at this point it seems sensible to make, because if you want to understand a physical process, it could be a materials failure process, for example, or if you need to make an engineering decision about, okay, is this weld fit for service? Are the stresses inside it low enough? Can we use this thing? Diffraction resolution is important for making that decision, but you don't really need the really high resolutions. In many cases, you don't really need the very high resolutions that are actually available in an ENGIN-X. In an ENGIN-X, you're taking a big hit in terms of counting time to enable that, which actually limits the types of studies that can be performed with it. So that's the kind of philosophy behind this proposal for EMAP. And this shows it in an overall strategy for engineering instrumentation at ISIS. So we will have still ENGIN-X for really high strain resolution studies, and we'll be able to reserve ENGIN-X for studies that really do need that high strain resolution. It can also do a bit of energy resolved imaging. It can also do a bit of sort of crystallographic texture analysis, but that's not its kind of main function. EMAP will be available for if you have very large components. You'll be able to sort of crane them in with a much larger beam hall there. If you've got a large device or a large manufacturing in situ manufacturing study, you'll have room for that in EMAP, and it will be fast. So you'll be able to do time resolved things very easily. And it will also have some texture characterization capability. And IMAT, just as now, it will be available for imaging and tomography. IMAT's currently having diffraction detectors fitted, so it will be the sort of primary instrument for crystallographic texture and spatially resolved crystallographic texture studies. And also it will have some limited strain capability, but at lower resolution. So that's kind of overall strategy. I've put a summary here, but I think the main thing is that more input is going to be needed from users to define the strategy for this. So I look forward to seeing some of you at the breakout room for engineering. I think it'll be interesting to see what the kind of user requirements are in a bit more detail. Thank you.